So today's lesson is really just a continuation of yesterday's, still talking about inverse functions. And really, a lot of what we're talking about today is stuff that we did cover yesterday. We just kind of need to formalize it. So we're going to jump right into an example here. It says, let f of x equal 2x minus 6. And remember that f of x we can really think of as y equals 2x minus 6. Okay? And so it says, write a formula for the inverse. Remember that notation means the inverse. Okay, so for the inverse, remember it's all about switching the x and the y. So we're going to start by rewriting that equation, but with the x and y reversed. And then you do want to make sure that you go back and solve for y, get the y back by itself. So I'm going to add the 6 to the other side, make this x plus 6 equals 2y. I think I may have even done this exact same example yesterday, so I apologize for my lack of creativity here. And then when I'm solving for that y, now I want to divide everything by 2, okay? Make sure that you divide each piece individually by the 2. And I'm going to rewrite this as 1/2 x, just because that's how we're used to writing it. If you wrote it as x over 2, that's okay. Plus, and then 6 over 2 is equal to 3, and this is what I would put down as my inverse, okay? So these two equations are inverses of each other, okay? This is the only thing today that's going to be a little bit new is these next two questions, and it's not even really new. If you remember this notation from a couple of days ago, this is a composite. So this is saying plug the inverse into the original function. Okay, so I'm going to take this 1/2 x plus 3, because that's really the function part of this, 1/2 x plus 3, and put it in place of x in the original equation. Okay, so that's going to look like this, 2, and then instead of x, I'm plugging in 1/2 x plus 3, and then I still need the minus 6. So if I simplify that by distributing the 2 times 1/2 would just make a 1, so that would be 1x, and 2 times 3 is 6. And then we still have this minus 6 hanging on out here. Okay? And now my plus 6 and minus 6 are going to cancel, and I'm left with just x. Okay? That would be my final answer for how that simplifies. So now let's try the next one. Remember that this process is not necessarily commutative. Okay, I can't count on these two things being the same. So when it asks me to do this again, I do have to actually work through it. This one is saying take the original function and plug it into the inverse. Okay, so now I'm going the other way. Now I'm taking the 2x minus 6 and putting it in place of x down here. Okay, so let's see what that's going to look like. That'd be 1/2, and then instead of x, I'm putting 2x minus 6. And then I still have my plus 3 on the outside. Let's distribute the 1/2. So 1/2 times 2 gives me 1, so that would be 1x. 1/2 times negative 6 would give me negative 3. And then I still have a plus 3. Okay? Negative 3 and positive 3 cancel each other out, and I'm left with just x again. That's sort of strange. Okay, and this next one, sketch a graph of f and its inverse. We very literally did this yesterday. Okay, so I'm not going to take the time to do this one again right now. But if you graphed these two things, you would find that each graph was a reflection over the line y equals x. We sort of discovered that yesterday, and then when we did an example similar to this, I did actually draw the graph so that you could see it was a reflection over y equals x. So because these are inverses, this should always be true. There'll be reflections over y equals x. Okay, I'm not sure if I left this next part in your notes or not, but I just want to kind of formalize everything that we just talked about. So these three properties are really, really important for you to know about inverse functions. And this first thing is referring to what we saw back here, is that if two things are inverses of each other, okay, if one is the inverse of the other. When you do the composite, meaning you plug one into the other, in both directions, it should cancel out and always just equal x. It doesn't cancel out completely. It doesn't make like a 0, but it leaves just the x by itself. It should work out exactly like this anytime you've got two things that are inverses of each other, okay? And the reason for that is we kind of talked yesterday about how inverses undo each other, okay? So when you have an inverse function, it's like you're stripping away all of the stuff that's been done to x, and x just is sitting there by itself, okay? So that's a really important one to note. That's worded differently in your book, but if you wanted to see what this looked like in symbols, it looks like this. The composite of f and its inverse is going to be always the same as the composite in the other direction, which remember we said is not always true, okay? But it is when you're working with inverses, and both of these things will always come out to equal just x. You have to test it both ways. Like if I hand you, this is a question you're going to be asked a lot. If I hand you two functions and say, are these two things inverses of each other? This is how you can tell, is by doing the composite and seeing if it comes out to equal x. But you have to test it in both directions, okay? Okay, and then the next one we talked about yesterday, but important to write down again. The graph of a function and its inverse will always be reflections over the line y equals x. And we mentioned this yesterday also. Domain and range of an inverse will always be reversed from the original because you're essentially switching the y's and the x's, so it should make sense that your domain and range are going to switch, okay? Okay. A couple more quick examples to talk through today. Example 2, sketch a graph of y equals x to the fourth, then sketch a graph of the inverse. We did a similar one yesterday, but that's okay. So y equals x to the fourth, that's a power function. It's an even power, right? So it's going to look similar to a parabola. Technically, it's going to be a little flatter on the bottom and a little steeper on the sides. But y equals x to the fourth would look something like that. Okay. If you didn't know that, you could put that into your calculator and graph y equals x to the fourth. Okay. And then we want to reflect over the line y equals x, which remember is that diagonal line that would go right up the center. Okay, so there's just the line itself for sort of a visual. So when we go to do our inverse is going to look something like this guy kind of turned on its side. Oh, and if I was better at this, I would have made that cross exactly, but. So my inverse is going to look something like that, and I'm just visually reflecting it over that line. And again, I probably should have had it intersect like right there, but that's okay. Okay, so is the inverse a function, and how do you know? You could answer this two different ways. You could say that the inverse itself, which is the green graph, I don't know if you can tell the colors, but the inverse fails the vertical line test. And I guess I should have said the answer here. The answer is no. This is not a function because it fails the vertical line test. Or remember, you could use the horizontal line test on the original graph. So the original x to the fourth, which was the blue one, fails the horizontal line test. Either one of those would be okay, but when you're using one of these two tests, you do have to make sure to indicate whether you're talking about the inverse of the original, okay? Because vertical line test passes for the original here. So if you just said it fails the vertical line test, I don't know if you're talking about the inverse of the original, okay? So make sure you specify inverse fails the vertical line test or the original fails the horizontal line test. And then this next question is sort of interesting. How could we restrict the domain of f of x so that the inverse would be a function? Okay, so let's think about what makes this inverse not be a function. It's because it's got this double branch, right? Because you can hit the line twice, okay? If I could magically get rid of this bottom branch, then I'd be working with a function again, right? So if I could somehow take and get rid of this bottom branch of this graph, then I would be okay. If I was just looking at this green line, then I could say, yes, it is a function, okay? Well, let's think about what that would mean would happen in the original graph. in the original graph, that means we would have to eliminate this, okay? Because that's the part that would reflect over and make this. So if we were only looking at this portion of the original graph, and that was a terrible job tracing that, then the reflection would come out to be a function, okay? And so what did I really do there by crossing off this part is I got rid of all of the negative x's, okay? These are all the negative x values. I eliminated them from my original graph. And so the restriction on the domain is we want to only look at x's that are greater than or equal to 0, otherwise known as the positive numbers. But remember that positive doesn't technically include 0. So positives plus 0 would be my restriction. So I can say in my original graph, if I only looked at x is greater than or equal to 0, then the inverse would still be a function, okay? And so sometimes we do that. Sometimes we say, you know what, we're working with this thing and it's inverse, but the inverse isn't a function and that's going to cause us some problems. So as far as our original graph goes, we're going to restrict it so that we're only looking at numbers greater than or equal to 0. Now, some of you might be thinking, why couldn't we get rid of that branch and only have the negative values? We could, technically. We just don't usually do that. We don't usually look at just the negatives. It's usually just the positives that we deal with. But technically, that's not wrong, okay? You could say that you're going to restrict it and only look at the negatives. So again, for a restriction, you're saying what part of the graph do you want to look at so that when you flip it, it stays a function, okay? Okay, that's really it for today. Like I said, a lot of what you talked about today was covered yesterday, so you should be totally okay to start working on your homework assignment tonight, which is section 8.3 from the textbook. That assignment is posted either in your homework packet or on the backboard in class.